November 14th, 1942. Philadelphia Navy Yard, Pennsylvania. A 2,700-pound steel projectile hung suspended above a 12.1-inch thick armor plate tilted at 19 degrees. The plate represented a precisely machined section of Class A face-hardened armor destined for the hull of USS Iowa, then under construction at the New York Navy Yard. Around the test fixture stood representatives from 3 steel companies, Carnegie, Bethlehem, and Midvale, each manufacturer having submitted armor samples for evaluation. Officers from the Navy's Bureau of Ordnance checked instruments. Engineers from the Bureau of Construction and Repair reviewed calculations one final time. Everyone present understood what this test would reveal. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The 16-inch Mark 8 armor-piercing shell about to strike this plate was the most powerful projectile the United States Navy had ever developed. Capped with hardened steel, filled with 40 pounds of explosive D, designed to punch through enemy battleship armor and detonate inside vital spaces. The armor plate below represented the primary defense of America's newest and fastest battleships, ships designed to escort carrier task forces across the Pacific at 33 knots. Ships that would face Japanese battleships, whose capabilities remained largely unknown to American intelligence in late 1942. The test would answer a question that had haunted naval architects since the Iowa-class design began in January 1938. Could the armor scheme developed for these fast battleships protect them against the very shells their own guns would fire? The answer, documented in classified test reports that would not be declassified for decades, was no. The armor could not, and everyone in that Philadelphia test facility would know it before the day ended. The story of Iowa-class battleship armor does not begin with a single brilliant metallurgist discovering a forbidden alloy. It begins with a compromise. A calculated gamble forced upon American naval architects by constraints that had nothing to do with metallurgical science and everything to do with speed, weight, industrial capacity, and the desperate urgency of 1938 when war in the Pacific seemed inevitable. Understanding what happened requires understanding what the Iowa class was designed to do, and more importantly, what it was designed not to do. The Iowa class was never intended to be the most heavily armored battleship. That distinction belonged to ships like the South Dakota class, which preceded the Iowas and featured more compact armor schemes concentrating protection over shorter citadels. The Iowas were designed first and foremost for speed to keep pace with the new Essex-class aircraft carriers that would form the striking power of the Pacific Fleet, speed to chase down Japanese fast battleships, speed to escape unfavorable engagements. That speed requirement, 33 knots minimum, drove every design decision. The ships needed length for their hull form to achieve that speed efficiently. 887 feet overall length. That length meant the armored citadel protecting magazines and machinery spaces stretched 512 feet, longer than any previous American battleship. More area to armor, more weight. The armored citadel of a South Dakota-class battleship was just 385 feet long. The Iowa's citadel was 127 feet longer, requiring substantially more armor plate to protect. The ships also needed powerful machinery. 212,000 shaft horsepower from 8 Babcock and Wilcox boilers driving 4 propellers through General Electric steam turbines. The machinery weighed thousands of tons. The fuel to feed that machinery weighed thousands more. Every pound dedicated to propulsion was a pound that could not be armor, and critically, the ships needed to fit through the Panama Canal locks, 110 feet maximum beam. This constraint was absolute. Without the ability to transit between Atlantic and Pacific, the strategic value of the ships would be crippled. The beam limitation directly affected armor arrangement. It constrained how much protection could be mounted without exceeding the dimensional limits or creating top-heavy designs with dangerous stability characteristics. These constraints forced the Bureau of Construction and Repair into difficult calculations beginning in January 1938. Captain A. J. Chantry led the initial design studies. The first concepts were wildly impractical. One early design featured 12 16-inch guns, 35 knot speed, and sufficient armor to stop only 8-inch cruiser shells. Displacement exceeded 50,000 tons. The design team quickly realized this approach was impossible. By late January 1938, 3 revised designs emerged. Design A carried 4 triple 16-inch turrets with reduced armor. Design B featured 3 triple turrets with better protection. Design C emphasized speed, with 300,000 shaft horsepower for 35 knots, but compromised armor coverage. Each design revealed the fundamental problem. To achieve 30-plus knots within Panama Canal beam constraints at reasonable displacement, armor protection would have to be carefully limited. The final contract design approved in June 1938, when President Franklin Roosevelt authorized construction under the Second Vinson Act, specified 45,155 tons standard. Displacement: 9 16-inch 50-caliber Mark 7 guns in 3 triple turrets, 12.1-inch main belt armor, inclined at 19 degrees, giving an effective thickness of 13.5 inches against horizontal shellfire. This armor scheme was explicitly designed to provide immunity against 16-inch 45-caliber shells, the type carried by earlier American battleships like North Carolina and South Dakota classes, at ranges between 18,000 and 30,000 yards. But the Iowa class would not carry 16-inch 45-caliber guns. The ships would carry 16-inch 50-caliber guns, firing heavier, faster projectiles. The 2,700-pound Mark 8 shell, leaving the barrel at 2,500 feet per second, had substantially greater penetrating power than the rate 2,240-pound Mark 5 shell the armor had been designed against. This created a profound contradiction at the heart of the Iowa-class design. The ship's armor could not protect against their own weapons at most battle ranges. The General Board of the Navy understood this limitation when they approved the design. Classified minutes from design review meetings show board members explicitly acknowledging the armor would not defeat the Mark 8 shell. They accepted the vulnerability because the alternative, adding enough armor for protection against the heavier shell, would increase displacement beyond acceptable limits and reduce speed below the 33-knot requirement. Speed was judged more valuable than invulnerability. But accepting the limitation required confidence in 2 assumptions. First, that Japanese battleships would not develop comparable heavy shells with similar penetration characteristics. Second, that American fire control and tactical doctrine would allow Iowa-class battleships to engage at ranges where their superior speed and radar-directed gunnery would provide advantage before enemy shells could strike vulnerable zones. Both assumptions were questionable in 1938. Japanese capabilities remained poorly understood by American intelligence. The existence of the Yamato-class super battleships with 18-inch guns was completely unknown. Even the capabilities of older Japanese battleships like Nagato-class remained uncertain. The General Board could only hope Japanese developments would not make the Iowa-class armor inadequate against foreign weapons as well as American ones. The armor itself represented the best technology available to American industry in the late 1930s, but that technology was not advancing as rapidly as foreign developments. This fact would become one of the most closely guarded secrets of American naval armor production, and one of the factors that made the Iowa-class vulnerability more severe than the raw thickness numbers suggested. Naval armor development had followed a consistent trajectory since the 1890s. Nickel steel replaced iron. Harvey face hardening, developed by American engineer Hayward Augustus Harvey in 1890, created hard surfaces resistant to shell penetration backed by tough metal that wouldn't shatter. German Krupp Company improved this with chromium additions and decremental hardening processes, creating Krupp cemented armor designated KC or Class A that became the standard for major battleship protection worldwide by 1900. By World War I, all major navies used variations of Krupp cemented armor. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The face of the plate was super carbonized, with carbon content raised to 1.0 to 1.5% through weeks-long exposure to carbon-bearing gases in sealed furnaces. This created an extremely hard face layer when quenched. Behind the face, the plate was softer, tougher, capable of absorbing impact energy without cracking. Typical composition was 0.35% carbon, 3.9% nickel, 2.0% chromium by weight. The face could reach 670 to 700 Brinell hardness. The back remained around 280 Brinell. American manufacturers produced Class A armor from this formula. Carnegie Steel, later Carnegie Illinois and eventually U.S. Steel, made Carnegie Krupp cemented armor, designated CKC. Bethlehem Steel experimented with Bethlehem non-cemented armor designated BNC that used different ratios and no face cementing. Midvale Steel developed Midvale non-cemented armor designated MNC with extremely thick, hard faces. Between World War I and the mid-1930s, American battleship construction halted under Washington Naval Treaty limitations. No new armor was manufactured for capital ships between 1923 and 1936. When armor production resumed for North Carolina and South Dakota classes in the late 1930s, American manufacturers faced a critical problem. British and German manufacturers had continued improving armor metallurgy throughout the 1920s and 30s, despite treaty limitations on ship construction. They developed temper processes and alloy refinements that made their World War II-era armor approximately 20 to 25% more effective than equivalent thickness American armor against large caliber projectiles. British cemented armor used in King George V-class battleships had superior resistance to shell penetration compared to American Class A of the same thickness. German Krupp cemented armor used in Bismarck and Tirpitz showed similar advantages. The American disadvantage stemmed from testing procedures, not inferior metallurgical science. American armor testing prioritized ensuring that shells would not penetrate intact and able to detonate. As American armor-piercing shells grew stronger through the 1920s and 30s, test standards required thicker, harder face layers to shatter those shells. The extremely hard face helped against weaker shells, but created brittleness problems against the most powerful projectiles, which could penetrate the brittle face in damaged condition rather than being kept out entirely. British and German testing methods did not emphasize shell destruction to the same degree. Their armor had somewhat thinner, less brittle faces, optimized to resist penetration rather than destroy projectiles. Against the powerful capped armor-piercing shells used by all navies in World War II, this difference meant British and German armor performed substantially better. American naval architects knew about this performance gap by 1939, when armor production began for the Iowa class. Metallurgical reports from European sources and testing of captured plates confirmed American armor was approximately 75 to 80% as effective as equivalent British cemented armor against heavy shells. Multiply the Iowa's 12.1-inch belt by 0.75. The result is effective protection equivalent to roughly 9 inches of British armor. This made the already marginal protection even more questionable. But changing the manufacturing process would have required years of development and testing. The industrial capacity to produce armor was extremely limited. In 1939, the United States could produce 75 million tons of steel annually, but specialized armor production capacity was only 19,000 tons per year. The special manufacturing required weeks of controlled heating, gas cementing, and quenching. Testing procedures for each plate batch added more time. Quality control was critical. Defects could create fatal weaknesses. With war approaching and multiple battleship classes under construction simultaneously, North Carolina, South Dakota, and Iowa classes, all competing for limited armor plate, the Navy could not afford delays for metallurgical experiments. The decision was made to proceed with existing Class A armor specifications, despite the known performance disadvantage compared to foreign armor. This decision was compounded by another development that occurred during the Iowa class design process. The Bureau of Ordnance changed the primary projectile specification. Original plans called for the 16-inch 50-caliber Mark 7 gun to fire the 2,240-pound Mark 5 armor-piercing shell. the same projectile used by shorter 45 caliber guns. But gun design calculations showed the longer barrel and increased propellant charge could achieve higher velocities with heavier projectiles. Engineers developed the Mark 8 super heavy shell, 2,700 pounds, 460 pounds heavier than the Mark 5. The increased mass, combined with high velocity, produced dramatically greater penetrating power. At 20,000 yards, the Mark 8 could penetrate 20 inches of steel armor plate. At 10,000 yards, penetration exceeded 26 inches against vertical armor at normal impact angle. The shell handling systems for Iowa-class turrets were redesigned to accommodate the heavier Mark 8 before any keels were laid. This meant the ships would carry and fire exclusively the more powerful projectile. But the armor specifications had already been ordered based on protection against the lighter Mark 5. Changing armor thickness would require complete redesign of the citadel structure. Weight would increase substantially, speed would decrease, the entire concept would unravel. The Navy faced an unpalatable choice: redesign the ships, accepting lower speed and higher cost and later delivery, or proceed with armor adequate against older shells but vulnerable to the ship's own weapons. Urgency decided the issue. War was spreading in Europe. Japan's expansion in Asia threatened American interests. The Pacific Fleet needed modern fast battleships as quickly as possible. Minor changes were made to armor on the third and fourth ships, Missouri and Wisconsin, increasing forward bulkhead protection from 11.3 inches to 14.5 inches, but the main belt remained 12.1 inches for all four completed ships. USS Iowa, BB-61, was authorized June 12, 1940. Keel laid June 27, 1940, at New York Navy Yard. The armor began arriving in 1941. Massive plates manufactured by Carnegie, Bethlehem, and Midvale. Each plate precisely machined to specifications, face-hardened through weeks of gas cementing, quenched and tempered, tested to minimum standards. But those standards were based on performance against older projectiles, not the Mark 8 super heavy shell that would be the ship's primary weapon. The Philadelphia trials in November 1942 tested sample plates from all three manufacturers against Mark 8 shells at various ranges and impact angles. The results confirmed what calculations had predicted. At ranges below 25,000 yards, Mark 8 shells penetrated the 12.1-inch Class A armor with disturbing regularity when striking at angles simulating belt impacts. The 19-degree slope helped somewhat, but not enough. The trials report, classified secret and distributed only to Senior Bureau of Ordnance and Bureau of Construction and Repair personnel, contained unambiguous conclusions. Iowa-class armor provided immunity against 16-inch 45 caliber Mark 5 shells between 18,000 and 30,000 yards as designed. Against 16-inch 50 caliber Mark 8 shells, the immunity zone was drastically reduced. Protection was marginal below 25,000 yards and non-existent below 18,000 yards, where shells struck with enough remaining velocity to defeat the armor. One test particularly alarmed observers. A Mark 8 shell fired at simulated 20,000-yard impact velocity struck a 12.1-inch plate at 20-degree obliquity. The shell penetrated, though it broke up during penetration. The explosive filler did not detonate properly, but fragments would have entered the space, behind the armor. In combat, such penetration could damage machinery, rupture fuel tanks, or penetrate interior bulkheads protecting magazines. Even failed penetrations created spalling, metal fragments breaking off the rear face of armor and spraying into protected spaces like shrapnel. The test report noted that British cemented armor of equivalent thickness would likely have stopped the same shell. The performance disadvantage of American armor made the Iowa-class vulnerability worse than dimensional specifications suggested. An Iowa-class battleship could fire shells capable of penetrating its own armor at battle ranges, while foreign battleships with comparable armor thickness might have better protection due to superior metallurgy. This information remained classified for decades. Public descriptions of Iowa-class battleships emphasized impressive armor thickness without mentioning the limitations. Naval historians writing in the 1950s and 60s often assumed 12.1-inch belt armor provided comprehensive protection. Detailed analyses comparing armor effectiveness between navies did not appear in unclassified literature until the 1980s and 90s, when researchers gained access to formally classified test data. The vulnerability had serious implications for Pacific War operations. If Iowa-class battleships engaged Japanese battleships at close range, they could not rely on armor to protect against enemy shells. Japanese 16-inch 45 caliber guns on Nagato-class battleships fired shells with penetration characteristics similar to American Mark V projectiles. Against these, Iowa armor would perform adequately, but if the Japanese had developed heavier shells, or if the unknown Yamato-class battleships carried weapons superior to anything anticipated, Iowa-class ships could face enemies whose shells would defeat their protection, while Iowa shells might not penetrate enemy armor if Japanese metallurgy proved superior. American tactical doctrine evolved to address this reality. Iowa-class battleships would rely on speed and radar-directed fire control to engage at advantageous ranges. Superior American radar developed during the war allowed accurate firing at distances where Japanese optical rangefinders were ineffective. Maintaining engagement range above 25,000 yards negated the armor vulnerability. Fire control radar could track targets and calculate firing solutions, while the ships remained beyond effective range of enemy optical fire control. This doctrine was never tested in major surface action. The Iowa class fought only one surface engagement during World War II. On February 16, 1944, during Operation Hailstone against Truk Atoll, USS Iowa and USS New Jersey engaged Japanese destroyer Nowaki at 35,700 yards. The ship straddled Nowaki with 16-inch shells, near misses causing splinter damage. Nowaki escaped due to extreme range and high speed. Iowa fired on and sank the Japanese training cruiser Katori during the same action. New Jersey helped sink destroyer Maikaze and auxiliary cruiser Akagi Maru. All engagements occurred at ranges where neither American nor Japanese ships faced severe armor penetration threats. The action validated American long-range gunnery doctrine but provided no data on close-range armor performance. Throughout the Pacific War, Iowa-class battleships served primarily as anti-aircraft escorts for fast carrier task forces. Their speed allowed them to keep pace with carriers. Their massive 5-inch 38 caliber secondary batteries and numerous 40mm and 20mm anti-aircraft guns provided excellent protection against Japanese aircraft. Their 16-inch main batteries were used predominantly for shore bombardment, supporting amphibious landings at islands including Kwajalein, Eniwetok, Saipan, Guam, Palau, Iwo Jima, and Okinawa. The lack of major surface actions meant the armor vulnerability remained theoretical rather than proven in combat. But the vulnerability shaped every operational decision regarding Iowa-class employment. Admirals commanding battleship divisions understood their ships could not safely engage enemy battleships at knife-fighting ranges. Doctrine emphasized maintaining distance, using radar advantage, and avoiding close-range gun duels that would expose the armor weakness. The vulnerability also affected post-war analysis of battleship design. When naval architects and historians evaluated World War II capital ship designs, the Iowa class received mixed assessments. The ships were praised for speed, endurance, radar integration, and effective anti-aircraft capability. But armor protection was consistently rated as marginal compared to foreign contemporaries and even compared to the preceding South Dakota class. British King George V class, with 14-inch main belt of superior British cemented armor, had better protection against heavy shells, despite thinner nominal thickness. German Bismarck class, with 12.6-inch main belt of German Krupp cemented armor, had comparable or better effective protection. Japanese Yamato class, with 16-inch main belt armor of excellent Japanese Vickers hardened plate, had vastly superior protection, essentially immune to American 16-inch shells at all practical battle ranges. The South Dakota class, with 12.2-inch belt over shorter citadel, had similar thickness to Iowa class, but concentrated that protection more efficiently. The more compact design of South Dakota-class ships meant less area to armor, allowing somewhat better distribution of protective weight. Though South Dakota armor faced the same metallurgical disadvantages as Iowa armor, the shorter citadel and lower emphasis on extreme speed produced a more balanced design. Some analysts argued the Iowa-class armor weakness was acceptable given the ship's intended role. As carrier escorts and fast commerce raiders, the Iowas were not designed to slug it out with enemy battleships in traditional battle line engagements. Speed was more valuable than maximum protection for ships that would spend most of their service escorting carriers or bombarding shore targets. The armor was adequate for the missions actually performed. Other analysts viewed the compromise more critically. The American industrial base could have produced better armor if development had been prioritized. British and German advances in armor metallurgy were known before Iowa-class construction began. The decision to proceed with inferior armor specifications rather than delay construction for metallurgical improvements represented a calculated risk that worked out favorably due to circumstances, primarily the lack of major surface actions, rather than sound design philosophy. The torpedo defense system represented another area where the Iowa-class protection proved problematic. The system was virtually identical to the South Dakota class, consisting of multiple liquid-loaded and void compartments designed to absorb underwater explosions equivalent to 700-pound TNT charges. This protection standard was based on intelligence estimates from the 1930s. American naval intelligence had seriously underestimated Japanese torpedo development. The Type 93 Long Lance torpedo, carried by Japanese destroyers and cruisers, had a warhead equivalent to 891 pounds of TNT, substantially more powerful than the 700-pound standard the Iowa-class torpedo defense was designed against. A Long Lance hit on USS North Carolina in September 1942 penetrated the ship's side protection system, flooding multiple compartments and causing serious damage. North Carolina survived, but required months of repairs. The Iowa-class torpedo defense, though slightly improved over North Carolina with closer spaced bulkheads and increased bulge volume, remained vulnerable to Long Lance torpedoes and potentially to German torpedoes as well. Post-war analysis showed the system would likely fail against modern weapons. When concerns about reactivating Iowa-class battleships arose in the 1980s, engineers discovered that full-scale tests conducted at Philadelphia Navy Yard had revealed serious weaknesses. The tests, conducted using decommissioned sections of hull structure, showed that the heavy Class B armor used in the inner torpedo bulkhead could not flex enough to absorb large underwater explosion pressures. The armor cracked at joints where bulkheads met the triple-bottom structure. The system could potentially fail catastrophically against multiple torpedo hits or against shaped charge warheads that might penetrate the bulge system and detonate against the armor belt from inside. These vulnerabilities were known but not publicized during the ship's reactivation in the 1980s. The Cold War Soviet Navy possessed submarines with advanced torpedoes far more powerful than World War II weapons. If Iowa-class battleships had faced Soviet submarines in combat, their underwater protection would have been grossly inadequate. 2 or 3 modern torpedo hits might have disabled or sunk these massive ships. The ships never faced that test. During their 1980s service, Iowa-class battleships operated primarily in shore bombardment roles during conflicts in Lebanon and the Persian Gulf War. During Operation Desert Storm in 1991, USS Missouri and USS Wisconsin fired Tomahawk cruise missiles and 16-inch shells at Iraqi targets. The ship's armor protected against return fire from Iraqi coastal batteries, but Iraqi weapons were relatively light, nothing approaching the penetrating power of battleship-caliber guns or modern anti-ship missiles. One incident during Desert Storm illustrated both the effectiveness and the limitations of Iowa-class armor. USS Missouri was hit by Iraqi anti-aircraft fire during a chaff defense incident involving USS Jarrett. A 20mm round from Jarrett's Phalanx close-in weapon system, fired at chaff, mistakenly identified as an incoming missile, struck Missouri. Most rounds bounced off the armor. One round penetrated the forward funnel, passing completely through the thin funnel plating. Another penetrated a bulkhead and embedded in an interior passageway. The incident showed that even thick armor had vulnerable points. The superstructure, funnels, and upper works were protected by thin special treatment steel or ordinary plating, not battleship-grade armor. These areas were vulnerable to relatively small weapons. The main belt and turret armor could resist tremendous punishment, but a modern battleship had thousands of square feet of structure not protected by heavy armor. Fires, equipment damage, and casualties could result from hits that never threatened the core armor scheme. The fundamental truth about Iowa-class armor was that it represented a conscious compromise in a design optimized for speed and operational flexibility rather than maximum protection. The ships could survive tremendous damage, as their robust construction and compartmentalization provided excellent damage control capabilities. But they were not invulnerable fortresses. Their armor could not stop their own shells at battle ranges. Their protection was inferior to foreign contemporaries. Their torpedo defense was inadequate against modern weapons. None of this diminishes the Iowa-class's significance. These ships served the United States Navy admirably for almost 50 years across multiple wars and conflicts. They proved adaptable, resilient, and effective in the roles they actually performed. But understanding their limitations is essential to understanding their real place in naval history. The myth of invulnerable American super battleships does not serve historical accuracy. The Iowa class was a very good design that made intelligent compromises to achieve specific capabilities. Those compromises included accepting armor protection that was adequate for expected threats and tactics, but not comprehensive against all possible threats. This was not a failure. It was a realistic engineering choice, made under severe constraints of time, weight, industrial capacity, and strategic requirements. The men who designed the Iowa class understood exactly what they were building. They knew the armor limitations, they knew the vulnerabilities, they accepted those limitations to gain speed and range and operational flexibility. In the event, those choices proved correct for the actual war the ships fought. But it is worth remembering that alternate histories existed where those choices might have proven fatal. If the Iowa class had faced Yamato in a surface action at 20,000 yards, American armor would have been penetrated by Japanese 18-inch shells, while American 16-inch shells might have failed to penetrate Yamato's massively thick belt and turret armor. American advantages in radar and fire control might have compensated, allowing hits before Yamato could return effective fire. But the outcome would not have been assured by superior protection. If the Iowa class had faced modern Soviet submarines in the 1980s, torpedo protection inadequate for World War II, long-lance weapons would have been completely overwhelmed by heavyweight torpedoes, carrying hundreds of pounds of high explosives and shaped charge warheads. The ships would have relied entirely on escorting vessels and countermeasures to prevent attacks, not on inherent armor protection. These counterfactuals matter because they reveal the reality beneath the mythology. Battleship armor was never absolute protection. It was always a calculated balance of thickness, metallurgy, weight, and industrial capacity, shaped by specific threat assessments and tactical doctrines. The Iowa-class armor was good, not perfect, effective, not comprehensive, adequate for the battles actually fought, not for all possible battles that might have been fought. The story of Iowa-class armor is not simply a story of steel plates and metallurgical formulas. It is a story of the people who made those plates, tested them, and trusted their lives to them. Understanding the human dimension reveals how engineering compromises translated into operational realities and how sailors lived with vulnerabilities they may not have fully understood. At Bethlehem Steel's plant in Lackawanna, New York, workers manufactured armor plates for the Iowa class beginning in 1940. The process required extraordinary precision and patience. Each plate began as a massive steel ingot weighing tens of tons, cast from molten metal in open hearth furnaces, heated to over 3,000 degrees Fahrenheit. The chemical composition had to be exact. Too much carbon made the steel brittle, too little reduced hardness. The nickel content at 3.9% provided toughness. The chromium, at 2.0%, enabled proper heat treatment. The ingots were forged under hydraulic presses exerting thousands of tons of force, compressing the metal, aligning grain structure, eliminating voids and inclusions. The forging process alone took days. The plates were then rough machined to approximate dimensions and moved to the cementation furnaces. There, buried in bone, charcoal, or exposed to carbon-bearing gases, the face of each plate absorbed carbon for 2 to 3 weeks. Temperature control was critical. Too hot and the carbon penetrated too deeply, creating brittleness throughout the plate. Too cool and the carbon layer remained too shallow. After cementation, the plates underwent decremental hardening. The face was rapidly heated to above the critical transformation temperature, approximately 1,500 degrees Fahrenheit, while the back remained cooler. Then the entire plate was quenched. First the superheated face with jets of oil or water, then both sides. The rapid cooling transformed the carbon-rich face into extremely hard martensite. The cooler back formed tougher structures that could absorb energy without fracturing. Workers then tempered the plates by reheating to moderate temperatures and slowly cooling. This reduced internal stresses and adjusted the final hardness to specifications. The completed plates were machined to final dimensions, drilled for mounting bolts, and tested. Sample sections were cut from each production batch and subjected to ballistic testing. Shells were fired at test plates to verify minimum resistance standards. Plates that failed testing were rejected. Accepted plates were shipped to the shipyards. The workers who made these plates understood they were creating protection for sailors who would face enemy fire. Many had sons or brothers in the Navy. The knowledge that defects could cost lives created intense pressure for quality. Yet the workers also knew the schedule pressure. War was coming. Ships needed to be completed quickly. Sometimes there were tensions between speed and perfection. Supervisors pushed for faster production. Quality inspectors demanded more testing. Compromises were negotiated. Most plates met specifications. Some were marginal but accepted because rejecting them would cause delays. At New York Navy Yard, where USS Iowa was under construction, workers installed the armor while the ship was still on the ways before launch. This was different from earlier practice where armor was installed after launch. Installing armor during construction allowed the heavy plates to be integrated into the ship's structure, with special treatment steel hull plating forming another layer of protection. The STS, developed around 1910 by Carnegie Steel, was high-tensile structural steel with armor properties comparable to Class B homogeneous armor, though in thinner sections. The main belt armor, plates, each weighing multiple tons, were lifted by cranes and positioned against the hull structure. The 19-degree inboard slope required precise angle measurements. Mounting bolts secured the plates to backing structures. Behind the main belt, multiple bulkheads subdivided the protected citadel. These interior bulkheads, though much thinner than the main belt, provided additional resistance to shell fragments and controlled flooding if the outer hull was penetrated. The deck armor consisted of multiple layers. A 1.5-inch special treatment steel weather deck topped the structure. Below that, the main armored deck combined 4.75 inches of Class B armor with 1.25 inches of STS for total protection of approximately 5.6 inches equivalent. Thickness. A 0.63-inch STS splinter deck below that caught fragments. Over the magazines, an additional 1-inch STS plate separated the magazine from the main deck above, providing extra protection against plunging fire. The turret armor was the thickest anywhere on the ship. The turret faces were 19.7 inches of Class A face-hardened armor. The sides were 9.5 inches. The backs were 12 inches. The roofs were 7.25 inches. Each turret weighed over 1,600 tons, fully equipped. The barbettes, the armored cylinders protecting the turret machinery extending down through multiple decks, were 17.3 inches thick, increased to 17.5 inches on Missouri and Wisconsin. The conning tower, the armored command post near the bridge where the captain and officers would direct the ship during battle, had 17.3-inch walls and a 7.25-inch roof. This provided protection for critical personnel and communications equipment. However, the conning tower was cramped, with limited visibility. In practice, captains often preferred to command from the open bridge during combat, despite the lack of protection, accepting personal risk for better situational awareness. The workers installing this armor understood its purpose but not necessarily its limitations. They knew the plates were thick, heavier than automobiles. They knew the steel was specially treated, harder than any commercial steel. Many assumed this massive protection made the ship nearly invulnerable. The classified test reports showing the armor could not stop the ship's own shells were not shared with shipyard workers or with most of the crew who would eventually serve aboard. USS Iowa was launched on August 27, 1942, christened by Mrs. Henry A. Wallace, wife of the Vice President. The ship slid into the East River amid cheers from thousands of spectators. Fitting out continued through 1943. Equipment, weapons, electronics, furniture, supplies, everything needed for a crew of over 1,800 men. The ship was commissioned on February 22, 1944. The crew that reported aboard Iowa included men from across America, farm boys from the Midwest, factory workers from the Northeast. Many had never seen the ocean before joining the Navy. They underwent training at facilities like Great Lakes Naval Training Station in Illinois or Naval Station Norfolk in Virginia. Gunnery training at specialized schools taught them to operate the massive 16-inch turrets or the 5-inch secondary batteries or the anti-aircraft weapons. For most crew members, the armor was simply part of the ship, like the hull or the deck. They lived and worked in spaces throughout the vessel, many far from the armored citadel. Crew berthing, mess halls, workshops, storerooms filled the interior. Some spaces were deep within the protected zone. Others were in the bow or stern outside the main belt. The men understood abstractly that the ship had armor, but few understood exactly where it was or what it could and could not stop. Turret crews worked inside the massive armored structures, 85 to 110 men per turret, divided between the turret proper and the handling rooms and magazines below. The turret interior was crowded, hot, filled with machinery. Hydraulic systems trained and elevated the guns. Shell hoists lifted projectiles from magazines 4 or 5 decks below. Powder hoists brought up the silk bags of propellant. Rammers pushed shells and powder into the gun chambers. Breech mechanisms closed and locked. During firing, the noise was tremendous, even inside the turret. The guns recoiled several feet with each shot, the entire mechanism absorbing the recoil force through hydraulic buffers. Powder smoke filled the turret despite ventilation. The men wore sound protection, but hearing damage was common among turret crews. Between shots, the crews worked frantically to reload. The design allowed 2 to 3 rounds per minute per gun when all systems functioned properly. The men in the turrets knew they were surrounded by 19.7 inches of armor on the face, substantial protection on the sides and back. They felt relatively safe. If enemy shells struck the turret, the armor should stop them. What they did not know was that at close range, a shell from an enemy Iowa-class battleship or from a foreign battleship with comparable weapons could potentially penetrate that turret face. The armor would resist, might deflect a shell striking at an angle, but a direct hit at optimal angle from close range could punch through. This information was classified. Even officers generally did not have access to the detailed test reports showing penetration capabilities and armor vulnerabilities. Captain John L. McCrea, Iowa's first commanding officer, understood broadly that armor had limitations, but the specific ranges and angles at which Iowa's protection could be defeated were not part of standard briefings. Tactical doctrine emphasized maintaining range and using radar advantage, which implicitly acknowledged armor limitations without explicitly stating them. The crew learned their ship through drills and exercises. Iowa's shakedown cruise in Chesapeake Bay in spring 1944 tested all systems. The 16-inch guns fired for the first time, shells arcing out over the ocean. The ship worked up to full speed, reaching 33 knots, the hull vibrating from the massive power of the turbines. The crew practiced damage control, firefighting, abandoned ship procedures, One aspect of damage control training involved understanding the ship's armor and compartmentation. Damage control parties learned which bulkheads were armored, which spaces were protected, how flooding should be controlled if the hull was penetrated. The training emphasized that even with heavy armor, the ship could be damaged. Shell hits outside the citadel could cause fires, equipment, damage, casualties. Near-miss explosions underwater could spring hull plates, causing flooding. The armor was protection, not invulnerability. USS Iowa departed for the Pacific in August 1944, joining the Fast Carrier Task Force. The ship's war service validated the design concept of fast battleships escorting carriers. Iowa could keep pace with the carriers at cruising speed and sprint to 30+ knots when needed. The ship's anti-aircraft batteries, including 25-inch 38 caliber guns in 10 twin mounts, plus numerous 40mm and 20mm weapons, provided formidable protection against Japanese aircraft. During the Battle of the Philippine Sea, in June 1944, before Iowa's arrival, the Fast Carrier Task Force destroyed hundreds of Japanese aircraft in what became known as the Great Marianas Turkey Shoot. Iowa-class battleships, New Jersey, and others provided anti-aircraft fire that contributed to the slaughter. The Japanese lost so many aircraft and pilots that their carrier aviation never recovered. American carriers and their escorting battleships dominated the Pacific thereafter. Iowa participated in operations against the Philippines in autumn 1944. The ship was present at the Battle of Leyte Gulf in October, the largest naval battle of World War II. During the battle, Iowa operated as part of Task Force 34 under Admiral Willis Lee, providing protection for carriers against possible Japanese battleship attack. The Japanese center force, including super battleship Yamato, approached through San Bernardino Strait, but withdrew before engaging American carriers. Iowa never came within gun range of Yamato. This was perhaps fortunate. Yamato displaced over 70,000 tons, fully loaded, far larger than Iowa's 57,000 tons. Yamato's armor included a 16-inch main belt of excellent quality Japanese Vickers hardened steel, plus 25.6-inch turret faces. American 16-inch shells would have had extreme difficulty penetrating Yamato's armor at any range. Yamato's 18-inch 45 caliber guns fired 3,200-pound shells that could penetrate Iowa's armor at virtually all battle ranges. A duel between Iowa and Yamato would have pitted American advantages in radar, fire control, and potentially speed against Japanese advantages in armor and shell weight. The outcome would have depended on who scored hits first and where those hits landed. Iowa's shells striking Yamato's superstructure or upper works could cause serious damage even without penetrating main armor. Yamato's shells hitting Iowa anywhere on the armored citadel would likely penetrate and cause catastrophic damage. American tactical doctrine was designed to avoid such duels. Multiple Iowa-class battleships would engage together, concentrating fire. They would maneuver at high speed, making it difficult for enemy ships using optical rangefinders to track them. They would use radar to fire accurately from extreme range before enemy ships could return effective fire. These tactics might have worked, but they were never tested against Yamato. After Leyte Gulf, Iowa participated in shore bombardment operations supporting amphibious landings. At Iwo Jima, in February 1945, Iowa's 16-inch guns shelled Japanese fortifications. The shells, each weighing as much as a small automobile, created massive craters and destroyed concrete bunkers. The Marines landing on the beaches faced fierce resistance, but pre-landing bombardment from battleships and cruisers had destroyed many Japanese guns and positions. At Okinawa in April and May 1945, Iowa provided gunfire support and anti-aircraft defense. Japanese kamikaze attacks targeted American ships relentlessly. Iowa's anti-aircraft batteries engaged multiple aircraft. The ship was never hit by kamikazes, but nearby vessels suffered damage and casualties. The constant alerts, the sound of anti-aircraft fire, the sight of aircraft burning and crashing created tremendous stress for the crew. Throughout these operations, Iowa's armor was never tested by enemy battleship fire. The armor protected against splinters and smaller weapons. During shore bombardment, Japanese coastal batteries occasionally returned fire, but their shells, typically 6-inch or 8-inch, could not penetrate battleship armor. Some shells struck Iowa and other battleships, causing minor damage to unarmored areas but bouncing off or shattering against the main belt and turrets. The crew developed confidence in their ship's protection through these experiences. They saw shells hit without causing serious damage. They saw the massive construction, the thick armor, the robust compartmentation. Many came to believe Iowa was nearly indestructible. This confidence was somewhat justified for the threats actually faced, but it might have proven false confidence if the ship had faced weapons designed to penetrate heavy armor. The war ended in August 1945 with Japan's surrender. The formal surrender ceremony on September 2nd occurred aboard USS Missouri in Tokyo Bay. Representatives of the Empire of Japan signed the instruments of surrender on Missouri's deck. Iowa was present in Tokyo Bay, part of the massive fleet that had brought Japan to its knees. The crew watched the ceremony, knowing they had been part of history. After the war, Iowa served in various capacities, training cruises, diplomatic missions, showing the flag. The ship was placed in reserve in 1949, joining the Atlantic Reserve Fleet. Iowa remained mothballed until 1951, when the Korean War led to reactivation. The ship deployed to Korean waters, providing gunfire support for United Nations forces. The 16-inch guns fired at North Korean and Chinese positions, destroying bunkers, artillery positions, supply depots. Iowa returned to reserve status in 1958 after Korea. The ship sat mothballed for over 20 years. During that time, naval warfare evolved beyond recognition. Missiles replaced guns as primary weapons. Aircraft carriers became larger and more capable. Submarines armed with ballistic missiles provided strategic deterrence. The battleship seemed obsolete, a relic of an earlier age. But in 1981, President Ronald Reagan's administration initiated the 600-ship Navy program. Part of this expansion involved reactivating the 4 Iowa-class battleships. The ships would be modernized with Tomahawk cruise missiles, Harpoon anti-ship missiles, and Phalanx close-in weapon systems for missile defense. The 16-inch guns and heavy armor remained relevant for shore bombardment and psychological impact. USS Iowa was towed to Avondale shipyards in Louisiana for modernization beginning in 1982. Workers stripped obsolete equipment and installed modern electronics, communications, and missile launchers. The modifications cost hundreds of millions of dollars per ship. 4 of the 10 5-inch twin mounts were removed to make room for missile launchers. The ship received improved radar, satellite communications, upgraded fire control for the main battery. The reactivation sparked debate among naval analysts. Critics argued battleships were vulnerable to modern missiles and submarines. The armor that had been marginal against World War II weapons was potentially useless against Cold War-era threats. Soviet anti-ship missiles like the SSN-19 shipwreck carried 1,000-pound warheads at supersonic speeds. Such missiles could potentially penetrate battleship armor or cause mission kills through damage to superstructure and systems, even without penetrating the main belt. Soviet submarines carried heavyweight torpedoes, far more powerful than World War II weapons. The Type 65 torpedo used by Soviet submarines had a warhead containing over 1,000 pounds of high explosive. Multiple hits from such weapons could overwhelm Iowa's underwater protection, designed against 700-pound charges. The ships would rely on escort vessels, helicopters, and countermeasures to prevent submarine attacks, not on inherent protection. Supporters of reactivation argued the ships provided capabilities no other platform could match. The 16-inch guns could deliver fire support from ranges of over 20 miles, far beyond what smaller naval guns could achieve. The Tomahawk missiles gave the ships precision strike capability against land targets hundreds of miles away. The psychological impact of battleships was significant, projecting power and deterring aggression. Iowa was recommissioned on April 28, 1984. The ship served in the Atlantic Fleet, participating in exercises in the Caribbean and Mediterranean. In 1987, Iowa deployed to the Mediterranean, visiting various ports, conducting training exercises with NATO allies. The ship demonstrated that despite being over 40 years old, the basic design remained viable for certain missions. On April 19, 1989, disaster struck. An explosion in Turret 2 killed 47 sailors. The blast occurred during a training exercise as the turret crew was loading powder for a firing exercise. The center gun's powder charges exploded, destroying the gunhouse and killing everyone inside. The explosion did not penetrate the turret armor, but the forces inside were catastrophic. The investigation concluded that improper loading procedures or possibly intentional sabotage caused the explosion, though the exact cause remained controversial. The tragedy demonstrated that even with massive armor, battleships remained dangerous to their own crews. The powder charges needed to propel 2,700-pound shells contained enormous energy. An accidental ignition could kill the entire turret crew, despite the protection of inches-thick armor surrounding them. The armor was designed to keep enemy shells out, not to contain internal explosions. Turret 2 was never repaired. The guns were removed, and the turret was sealed. Iowa continued operating, with only turrets 1 and 3 functional. The ship participated in Operation Desert Storm in 1991, though by then Missouri and Wisconsin were the primary battleship contributors. Iowa provided presence in the Red Sea, but did not fire in combat. After Desert Storm, with the Cold War ending and defense budgets declining, the decision was made to decommission all 4 Iowa-class battleships. Iowa was decommissioned on October 26, 1990. The ship was placed in the reserve fleet, moored with other mothballed vessels. For 20 years, Iowa sat in storage, while debates continued about whether the ships might be reactivated again. In 2011, Iowa was stricken from the Naval Vessel Register and donated to the Pacific Battleship Center. The ship was towed to Los Angeles, where it became a museum ship, opening to the public in 2012. Visitors today can walk the decks, enter the turrets, see the armor, and learn the history. The ship remains impressive, a monument to an era when massive guns and thick armor defined naval power. USS New Jersey, USS Missouri, and USS Wisconsin also became museum ships, preserved in Camden, Pearl Harbor, and Norfolk, respectively. Together, they represent the end of the battleship era. No nation has built a battleship since World War II. Missiles and aircraft rendered them obsolete for fleet combat. Their armor, once considered the ultimate protection, became a liability, adding weight without providing adequate defense against modern weapons. The lessons of Iowa-class armor extend beyond the specific ships. The story illustrates fundamental truths about military technology and engineering. First, protection is always a compromise. No armor can stop all possible threats at acceptable weight and cost. Designers must make choices about what threats to defend against and what vulnerabilities to accept. Second, perfect security does not exist. The Iowa-class armor was thick, well-manufactured, properly installed, yet it could not protect against the ship's own weapons at battle ranges. The designers knew this and proceeded anyway, because the alternative, designing slower ships or delaying construction, was judged worse than accepting the vulnerability. Third, industrial and metallurgical limitations constrain what is possible. American armor in World War II was inferior to British and German armor because American testing methods and production practices had evolved differently. Changing these methods would have required years of development time that was not available. The Navy had to work within the constraints of existing industrial capacity. Fourth, unused capabilities remain theoretical. The Iowa-class armor vulnerability to 16-inch shells was never tested in combat. The ships never faced enemy battleships at close range. The theoretical weakness remained theoretical. In the actual war fought, the armor was adequate. This raises philosophical questions about whether vulnerabilities that are never exploited actually matter. Fifth, technological evolution makes even the best designs obsolete. The Iowa-class armor that was marginal against World War II shells became irrelevant against Cold War missiles and torpedoes. The ships were reactivated in the 1980s because their guns and missile armament remained useful, not because their armor provided meaningful protection against modern threats. The metallurgists and engineers who developed Class A armor in the early 20th century did remarkable work. Krupp cemented armor represented cutting-edge metallurgy for its era. The face-hardening process, the alloy composition, the heat treatment procedures all reflected decades of research and refinement. American manufacturers produced millions of tons of this armor, protecting battleships, cruisers, and other warships. But they were working within constraints they could not overcome. Carbon, nickel, and chromium steels have finite strength. Face hardening creates brittleness along with hardness. No tempering process can eliminate this trade-off completely. British and German metallurgists found slightly better balance points, producing armor that performed about 25% better than equivalent American plate. But even the best World War II armor had limits. Modern armor materials like composites, ceramics, and reactive armor provide different protection mechanisms, but they too have limitations. No material is impenetrable. Every protection system can be defeated by sufficient force applied properly. The history of armor is a history of incremental improvements and evolutionary dead ends, not revolutionary breakthroughs that make protection absolute. The Iowa-class battleships, despite their armor limitations, served the United States Navy honorably for almost 50 years. They fought in World War II, Korea, and the Persian Gulf War. They provided gunfire support for Marines landing on hostile shores. They escorted carriers across dangerous waters. They showed the flag in peacetime, demonstrating American power and commitment. The men who served aboard these ships, over the decades, numbered in the tens of thousands. They lived with the ship's quirks and limitations. They maintained the machinery, fired the guns, stood the watches. Many formed deep attachments to their ships, considering them homes and comrades. Veterans associations for each Iowa-class battleship remain active, keeping alive the memories and maintaining connections among crew members. The armor plates they depended on, those massive steel structures weighing thousands of tons, did their job. They protected against the threats actually encountered. They provided confidence to crews who needed to believe their ship could withstand enemy attack. They symbolized strength and security, even if the reality was more nuanced than the symbol suggested. Today, the 4 Iowa-class battleships sit at their museum berths, silent and still. The armor remains, rusting slowly despite preservation efforts. Paint flakes, salt air corrodes. Time inexorably degrades even the mightiest steel. The ships will not fight again. Their armor will not face enemy shells. They exist now as monuments, reminders of a time when battleships ruled the oceans and armor thickness measured a nation's naval power. The visitors who walk their decks, children and adults, veterans and civilians, encounter physical history. They can touch the armor, feel the thickness, imagine the protection it provided. They can enter the turrets, see the massive guns, understand the scale of these weapons. They can read the plaques, explaining the ship's service, the battles, the men who served. But they cannot fully understand the compromises and calculations that went into the armor design. They cannot know about the Philadelphia test reports showing penetration vulnerabilities. They cannot grasp how American metallurgy lagged behind British and German developments. They cannot comprehend the complex engineering trade-offs between speed and protection, between cost and capability. This is perhaps appropriate. The ships as monuments serve a different purpose than the ships as historical artifacts. Monuments inspire, educate broadly, create connections across generations. Historical artifacts reveal complexity, demonstrate limitations, teach nuanced lessons about technology and decision-making. Both purposes have value. Museums can serve both functions if they are willing to tell complete stories rather than simplified myths. The complete story of Iowa-class armor is not a story of forbidden alloys or miraculous metallurgy. It is a story of competent engineers working within severe constraints to produce adequate protection for ships designed primarily for speed and operational flexibility. The armor was good enough for the war actually fought. It might not have been good enough for all possible wars. The difference between those two statements contains important lessons about risk, engineering, and the nature of military technology. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.